Welcome to the first lecture of the Danish IAS for the year. Oh, sorry. That's great. It's great to see all of you, the newcomers, the people that have been here before, and also the new assistant professors from the Danish IAS. There are already many here. You will have the chance to introduce yourself afterwards. There is a little reception, so please greet everybody. I want to welcome Kari. Kari Rummukainen is a professor at the University of Helsinki. And Kari is one of my favorite researchers. He's outstanding and has been doing great work prevalently in lattice quantum field theory, but applying to many different things, from QCD and the temperature all the way to gravitational waves and what you can do with that. As you know, there's been a Nobel Prize in gravitational waves this year, and I'm sure Kari was going to talk about that. The list of achievements and successes and prizes that Kari has got is immense, so I won't really bore you with that. Let's just say that he's been assistant professor in Dita. That's when I first met him, when I came from the States. And then he's been CERN fellow, CERN staff member. And then he's been Rummukainen, and again as assistant professor. So I will say that there is, besides his outstanding pedigree, he is actually a really fantastic researcher. I leave the floor to Kari, and thank you for coming here.
Thank you, and thank you for the invitation. I've been here a few times before, but not nearly as often as I would have liked to. I mean, because of all kind of work-related issues that one cannot always come to the meetings here. And but I have been, as Francisco mentioned, I mean 5 years in Denmark, in Copenhagen, as a kind of at the turn of the millennium, as an assistant professor. And today I'm going to talk about gravitational waves from the early universe, and what can we do with them? Can we observe them? And what they can tell us about physics. First, I would like to ask that how many of you are not physicists? Okay, good, great. My talk, I'm ashamed to admit, there are few formulas in there, but in principle it should be understandable. I mean, interrupt me if you want to ask questions. So, as you all know, I mean, a couple of years back there was a literally earth-shaking event on 14th of September at 11:45 on local time. A pulse of gravitational wave went through us all and literally moved us all. It was a very moving event. And those were observed. That was the first observation of gravitational waves, observed by the LIGO gravitational wave detector. And this originated from merger of two black holes, about 36 and 29 solar masses. They were orbiting each other and losing energy and spiraling faster and faster, boom, hitting each other. And that causes huge amplitude of gravitational wave. It was far away. I don't know how far away it was, but really in a cosmological distance from us. But nevertheless, the signal was so strong that it was detectable on these detectors, and those waves are the kind of the signal from the two different detectors. And this really opened a new window to the universe. First time gravitational waves have been observed. It was very appropriate because it was almost exactly 100 years before this observation when Einstein predicted gravitational waves. So it took really 100 years to observe it, and 101 years for the birth of the general theory of relativity, which kind of contains all of these solutions. And of course, in due course, these people who were the main culprits in this endeavor of detecting these gravitational waves got the Nobel Prize last year. Yes, Yeah, I mean, the detection of gravitational waves is a long history. As I mean, well, when I was a school kid, people were already trying to detect gravitational waves, but of course, I mean, in hindsight, it was hopeless task. They didn't have the technology. But during the decades since, I mean, of course, things have changed, and finally, this remarkable achievement was achieved. And currently, there are active gravitational wave detectors around the world. Here are the American LIGO detectors in Washington and what state was that? I forgot now. Louisiana, not Louisiana. Yeah, it was in Louisiana. Yeah, yes, near New Orleans. And Advanced Virtue detector in Italy, and these three form a collaboration kind of. They are synchronized detectors. In Japan, a new detector Kagra is being built, is soon coming online. In India, similar detector is planned, like India, and in Germany there's a smaller detector, but it's too small to see really anything. It's more like a technology prototype. And how these work, I mean, this is kind of the picture of one of the LIGO detectors in Washington State. You have two arms, which are 4 kilometers of length, orthogonal to each other, and laser beam is sent along these arms and reflected back. It's like here, I mean, there's a laser beam splitter, and which splits the beam in two arms, and they are reflected back and combined again here. And when things are kind of at rest, in quotation marks, these beams cancel each other somehow. The wave crests emerge here so that they are exactly opposite of each other, and you have no signal here. However, when the gravitational wave comes, what does it do here? It moves freely floating objects slightly. It kind of shrinks and expands the space-time. These mirrors here at the end are suspended so that they can move freely. They are suspended and isolated extremely carefully. And when a gravitational wave comes, it slightly wobbles this and that one, but to opposite directions. Boom, 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 boom. There's a nice animation what you can find in YouTube here. And it means that these don't exactly anymore cancel. So you get some signal here, and that's then what you measure. This is of course extremely simplified. Actually, the laser beam bounces back and forth several hundred times in order to amplify the effect, and they are all kind of fine-tuned there. And the strain is just astounding. Strain is the relative change in the length. It's 1 part in 10 to the 20. Which means that even though this is 4 kilometers, the movement here is less than the size of the atom, is less than the size of the nucleus of the atom, is 1,000th of the size of the proton. And you can still observe it. And somehow, I'm a theorist, so to me it seems impossible. I mean, if somebody tells me that you can measure distance to 1,000th of the size of the proton, I would say, forget it. Doesn't work. But that's part of the reason why it took 100 years to really observe this. Of course, the reason why you can observe such a small movement, I mean, atoms are coarse lumps, but when you have a huge amount of atoms, like in a big mirror, then you can see the collective movement much more accurately than the single atom size. So, sources. Where do these originate, this gravitational wave? And astrophysics is, of course, the primary source what these instruments are now doing. Binary compact object mergers. Binary compact objects are kind of two binary systems of very heavy stars, like black holes, which are the most densest objects, or neutron stars, which are the second most densest objects in the space. And indeed, this LIGO and virtual collaboration has now seen 5 black hole pairs, or at least published 5. They might have seen more. And actually one, which is kind of comme ci, comme ça, I mean halfway event, halfway might be not an event, so that they don't say that it's certain. But one collision of neutron stars also, which was published last year, last fall. And that has already had a big impact. I will tell you about it a bit later. Supernova are also a source of gravitational waves, but nothing has been yet observed, and one can argue that, okay, LIGO cannot see, it's not sensitive enough, or the supernova should be very close to us. And that can happen, but supernovas are not so common objects at the, let's say, within our galaxy or within the next galaxy, so that they could be observed. These black holes are not too common. I mean, these big black holes here are not too common objects, at least binary systems, but because the signal is so strong, you see them extremely far away. That's why they have seen already 5 of them. However, while these are, of course, the things what the astronomers are excited about as a particle physicist, I'm more excited about another source of gravitational wave, the early universe. And one talks about primordial gravitational waves. Because in a Big Bang, of course, the universe starts in an extremely hot, dense system and expands rapidly and cools. And you can expect that violent events may happen there. And those can generate gravitational waves. Gravitational wave production is strongly enhanced when you have a large energy density. It's really kind of strongly dependent on the energy density. That's why, although I'm waving my hands, I'm producing gravitational waves all the time. They have no effect on you, or, well, not observable effect, because the energy density is so small. But when you have black holes which are doing this kind of movement or spiraling each other, energy densities are huge, and that's why they are strong producers of gravitational waves. Early universe, the energy densities were enormous. I mean, they were millions of times larger than in, let's say, normal matter energy density, or billions of times. It's much easier to produce gravitational waves. And those then, having been produced, then are just propagating through the universe and waiting for us to detect them. That's exactly similar way to the famous microwave background, which was already also produced at the early universe, and now it is being observed. Now, one interesting fact is that the known physics, the standard model of particle physics, which contains all of our theories which we know about, cannot produce gravitational waves. Okay, so you would say, okay, then you don't have these things, which is possibility. However, if you observe gravitational waves from early universe, then it tells you, okay, there must be something which is not within our standard model. Some new physics theories, which there is plenty of room in the nature for new physics theories. We just haven't observed that, because of the limited energy range, what we can do on Earth. So, observation of these primordial gravitational waves would be a signal of new physics beyond the standard model. And I think it's almost certain that if this thing happens, if they are observed, I mean, that's an almost certain Nobel Prize for the people who did this observation. This is complementary with the particle physics searches on accelerators, in the sense that now you look at the different phenomena, and in principle you can reach much higher energy, because early universe you had almost arbitrarily high energy, not arbitrarily high energies, but enormously high energies available, which are not just possible to do technologically on Earth, so that much more exotic events might have happened than we can ever produce on particle accelerator. And one particle physics outcome already has been produced by these gravitational wave observations. The dense nuclear matter equation of state. I mean, the neutron stars are here, 2 neutron stars. Of course, these are the remnants of the supernova star explodes, and if it is not too big, it might, so that it collapses in the black hole, it might produce a neutron star, which is essentially a star mass atomic nucleus. It's so dense gravitational pull is so strong that all the matter compresses to atomic nucleus density. It is in principle like an atomic nucleus, but its mass is about 2 solar masses or a bit more. and how it behaves depends on the strong interactions and the nuclear matter equation of state, one says, that how it behaves. When you compress, how much it resists the compression. And that this is notoriously hard question. We don't have good tools to analyze this theoretically. Experimentally, we cannot do it on Earth. I mean, you don't have a hydraulic press which can produce neutronic matter. I mean, no way. And not even in explosions. I mean, you can even explode, let's say, atomic bombs or fusion bombs and try to produce that. It doesn't work like that. You don't get enough density. You can only get this kind of density at the scale of atomic nucleus when you, let's say, smash 2 atomic nuclei together, but you don't reach this high density what is in this neutron star. And the thing is, this is kind of funny picture. This is the radius of the neutron star versus the mass of the neutron star, mass in solar masses. And this is the theoretical band of uncertainty. And as you see, I mean, there's a huge range of uncertainty on the radius of the neutron stars. For example, this 1.5 solar masses, it could be somewhere here. Almost factor of 2. And there are no observations, direct observations. I mean, how can you tell if some object in sky is 14 kilometers or 9 kilometers when it is in somewhere and the other side of the Milky Way? I mean, there's no way. However, when they collide, of course, they approach each other, they deform each other, and you can deduce the stiffness of the matter, the size of the stars. And that constrains now your equation of state. And for example, this red band, there has been one observation of neutron stars. We know that this red band here cannot be realized in nature. So already one observation has limited the allowed radius and mass relation of the stars. This blue band actually is excluded because we know that they are heavier than 2 solar mass neutron stars, and that cannot support this. It's kind of funny actually, when you look at the neutron stars here, mass radius relation. If you have a 2 solar mass neutron star here, it has, assuming that this boundary is the correct equation of state, it is about 12 kilometers of radius. You took stuff out of it, so make it lighter. The radius doesn't change. It somehow, because you take mass out of it, the gravitational pull weakens, it expands. And its radius is practically constant here, until it becomes kind of very light, and then it's not anymore being pulled to the atomic nucleus density. It starts to expand rapidly to the, let's say, normal star stellar density, so it becomes, of course, thousands of millions of kilometers at some point. So that, well, not millions, whatever is the solar radius. But there's a big uncertainty, and when we get more observations, of course, I mean, this can be pinned down. And from the theory of strong interactions, it's very, very hard to do these calculations. Numerical lattice simulations are the best tool to study these interactions, but at high density they don't work because of so-called notorious sign problem. I'm not going into that here. But let us look at the events in the early universe. Thermal history. We are here. That now. The universe, the average temperature is 2.7 Kelvin, close to absolute zero temperature. Of course, space is cold. Space is cold. And here is the time, age of the universe in a logarithmic scale. And for example, all of the stars formed here, so that and the galaxies, etc., life formed here. All interesting stuff for us, I mean, happened here, very close to the present time here. But you have lots and lots of logarithmic time for particle physics events to happen. Somehow, when you plot it in a logarithmic scale, it becomes somehow jumps in your face that most of the universe was actually very hot and dense early universe state. So here is the galaxy formation. Universe is about hundreds of millions, billion years old. This is the famous microwave background was emitted here. If I go backwards here, heat up kind of the universe, at that temperature the electrons are kicked off of the atoms, atomic nucleus. So that at earlier times here, it was so hot that the matter was fully ionized. If you were sitting on a spacesuit there at that age universe, you wouldn't see anything because you have free electrons and an atomic nucleus. It's like sitting in milk. I mean, it's completely opaque, glowing, white-hot stuff. Light doesn't propagate. But when the universe cooled, after this point, electrons were captured, and suddenly the universe became transparent for light, and this microwave background then was free to propagate through the universe, and now we observe. When we go backwards, here's 1 year old universe, 1 hour old universe, nothing much interesting happens here. Then here, about 1 minute time scale, nucleosynthesis happened. Atomic nuclei were formed, so that when we go backwards, the nuclei are split apart here. So you get free protons, free neutrons. Oops, I went to here. And when we go even backwards 1 second, there was interesting things about neutrinos, but I don't talk about that. Here, then, when we are at the microsecond level, age of the universe, so-called QCD phase transition happened, which means that if we go backwards now towards earlier universe, the protons and neutrons melt into quarks and gluons. We get so-called quark-gluon plasma at higher temperatures. At higher temperatures. And when we go even further back, 1,000 times higher temperatures, we get so-called electroweak phase transition temperature, where one can say that the so-called Higgs field turned on, where the Higgs mechanism acted. And many interesting events may have happened there. We are not sure. For example, the baryon number, or simply matter of the universe, may have been generated during that. And gravitational waves may be produced here, depending on the properties what happens here. The known physics is here. I mean, what we know, the standard model contains all of this stuff. I mean, the closer to the Big Bang, I mean, Big Bang is principle here at the minus infinity, you go, the less you know for certain about these things. and kind of here is where our knowledge stops. The particle accelerators are just able to reach this level, but not higher. We don't know the details what happened there. And these 2 points, which I have kind of highlighted here, are possible points for the phase transition in the early universe. And those can produce gravitational waves. Even earlier times, I mean, we know little, I mean, nothing for sure, and lots of speculations, of course, all kind of interesting stuff. Let's say inflation might have happened here, which is this explosive expansion of the universe, where there are lots of kind of indirect evidence that might have happened, but it's by no means certain that happened there. I'm not going to talk much about that inflation here. And here we finally reach Planck scales, where all kind of string theories, etc., then take over, and even less is known. Now, particle accelerators can probe physics just at here. If there is kind of events which produce gravitational waves, we can probe all the way here, and even inflation with gravitational waves. So that it's a probe which can reach huge energy scales. And the sources of these gravitational waves, inflation is one of them, what I mentioned. And some of you might remember, at least physicists, particle physicists, this bicep thing a few years back, which was, they studied this microwave background radiation, and they observed one particular polarization pattern for it. And that pattern arises naturally if there are gravitational waves during this inflationary process, this kind of whirling pattern of polarizations. However, that turned out to be a mistake, or probably a foreground contamination, so some stuff in between, I mean, in our galaxy or interstellar matter can have produced that, so that that kind of went away. But I mean, things are going on there. So-called cosmic strings are also very strong producers of gravitational waves. If you have some kind of very exotic phase transition, you can produce vortex lines. You see those in, for example, liquid crystals when you do phase transitions, or superconductors already in condensed matter. Similar lines could be produced there, which kind of vibrate like guitar strings and make loops and string away. They can produce gravitational waves, but I'm not going to talk about those either. They are very speculative theories. First of the phase transitions are kind of well established. They happen, of course, all around us. Water boils, freezes. Those are first of the phase transitions. And they can happen in particle physics theories. But unfortunately, they do not exist in standard model. There are two candidates where it could be in this so-called QCD transition and electroweak transition. But now we know that they are not first order. When I was a student, or when I started studying, I mean, it was still open question whether these are first order or not. But now it has vanished for both. But strong transition is still possible in many extensions of the standard model. I mean, these new physics theories, exciting theories which have new particles and interactions. There are many candidates. And observing this gives a direct snapshot of the universe at the time when they were created, generated. Because when the gravitational waves are generated, they proceed to the universe basically without any interaction of the matter. So that they really, when they are emitted, they interact so weakly with the matter. That's why they are so hard to observe, that they basically don't care about whatever medium they are going through. Expected frequency for the gravitational waves from the early universe is about millihertz range. So basically, one oscillation in an hour. So the frequency is pretty low, but still technically doable. I mentioned here the standard model status. Here we know now, didn't know, let's say 30 years ago, what happens in the standard model. We have a theory of strong interactions called QCD. It has quantum chromodynamics. It has a phase transition at 170 MeV. Phase transition in quotation marks, because it's not really, strictly speaking, it's a smooth crossover. Phase transition would mean that there is some kind of discontinuity or non-smooth behavior. And what happens in this transition is that the hadrons, our protons, neutrons, and all other hadrons melt into quark-gluon plasma, which is kind of porridge of quarks and gluons. And this is now routinely produced in particle accelerators. I mean, you smash two atomic nuclei, let's say gold or uranium, or big enough atomic nuclei in particle colliders to each other. It produces a tiny blob of this quark-gluon plasma. Of course, it expands and freezes immediately, but you can still study the physics of this plasma that way. And there is no first order transition there. Theoretically, I mean, one can study this using lattice QCD simulations, and that is well established. 1,000 times higher. These units are now in particle physics units. I mean, it doesn't mean anything to print them in Kelvin, so that I didn't try even to convert. But this is 1,000 times higher temperature than this. This is mega electron volts, giga electron volts. And here the Higgs field turns on. And one can, I mean, typically, I mean, shows this as a cartoon, kind of the Higgs, so-called Higgs potential, which is at high temperatures has a minimum at the zero. At this temperature, it develops another minimum blob, and the Higgs Higgs kind of drops in this Noether minimum, and at zero temperature at our present day universe, I mean it sits here. And for the functioning of the standard model, it's essential that the Higgs is somehow here at the non-zero value of the potential. This, for example, gives for masses for the elementary particles. And this could have been first order, so that this jump could have been abrupt at some temperature, but it turns out now that it's a smooth crossover. It was in the 20 years ago, I mean, I was involved in many of the calculations where we studied this, and with the physical Higgs mass, Higgs was now found at LHC at CERN 5 years ago, and it's so heavy that it cannot be first order. There's also connection with the matter of the universe, so-called baryon number here, that at these high temperatures the baryon number can actually change. It's not fixed. Here at low temperatures the matter cannot vanish, floats to empty air. I mean, matter is stable as far as we know. I mean, we haven't observed any decay of protons. However, at this very high temperature that is possible, and so that there is a possibility that the matter is created during this process. But it's a very complicated and standard model cannot do. One can kind of quantify this by plotting the pressure of the matter, I mean particle matter as the units of temperature. If I just heat up space, volume, to higher and higher temperatures, this band is where the QCD phase transition happens, 100 MeV, and this is where the electroweak phase transition happens. It's a completely smooth and not much features in this phenomena. This is 2006, 10 years old, but and it has slightly changed, but I mean no conclusion. Conclusions are the same here anyway. So this is, yeah. No phase transitions there. But this Higgs field transition, what I showed, in the standard model it was smooth, no transition at all. But it's not certain that the standard model is the model which describes this. There could be something else besides the standard model there, because we haven't been able to study it conclusively in the particle accelerators. There's lots of room for kind of enlargements. And in some, these are called extensions of the standard model. And these can have a first order phase transition. Or you can have a new theory which comes in at still much higher energies than the standard model or the electroweak scale, and that can have phase transitions. And if the phase transition is a first order, like the boiling of water at normal pressure, it proceeds through bubble nucleation. So that imagine that we are in this hot phase, and we are cooling it down towards this critical temperature, the temperature where this transition would happen, like with the vapor, liquid water, I mean 100 at the normal pressure, 100 degrees centigrade. When we cool down to this temperature, nothing happens at that temperature, because first of the transitions have always metastability. There's a barrier for anything to happen. You have to cool down it, supercool, or superheat if you go the opposite direction. You supercool, and the stronger the transition, well, usually the stronger the transition is, the more you can supercool, until it becomes kind of probable to nucleate bubbles of the new phase. They are microscopic at the beginning. Like the boiling of water, you get tiny droplets which starts to expand. And then these droplets, because they are the favored phase, after all, they start to rapidly expand and cover then the whole phase. Boom, and the transition is complete. This is a violent process if you have a big energy densities involved here, and that produces gravitational waves. These are actually snapshots of our numerical simulations of this process. So I mean, on these particle physics experiments, we don't have any sign of beyond the standard model. This BSM means beyond the standard model, meaning that something which is not in the standard model of our particle physics. There are hints, of course, we already know there are hints of beyond the standard model physics, like the dark matter, which is seen in gravitationally in the galaxy movements. It's probably some exotic particle which doesn't belong to the standard model. But we haven't been able to catch it, I mean see it. I mean we just see that they start in space. But this would kind of give a completely new angle to this BSM therapy. And what is the instrument which we can use here is LISA, which is a similar interferometer as the LIGO, but now in space. It's a triangular constellation of 3 satellites, which are 2.5 million kilometers from each other on a present kind of a technological document. They are shooting laser beams to bomb between each other's back and forth and measuring the distances from each other. This is a huge distance, by the way, 10 times Earth-Moon distance. So it's an enormous constellation. Of course, there's no matter here. I mean, it's in vacuum between the satellites. They are just pointing lasers to each other, and they are able. These are able to measure the distances to each other again to 1 part, better than 1 part in 10 to 20, or 1 and 20 zeros, which means that better than the atomic size. I mean, distance measurement across 2.5 million kilometers. I just cannot believe that that's possible. It's so sensitive that I mean the spacecraft cannot be kind of just lasers anchored there. They have an internal part where the lasers and the receivers of lasers are, and an external part which doesn't touch the internal part. So the external part kind of isolates the internal part from space. I mean, because you have radiation, solar radiation, some dust particles in space. This external part kind of keeps itself positioned somehow so that the internal part doesn't touch the wall, so that the internal part is freely falling, surely, and nothing disturbs it. And the scheduled launch is 2034. I mean, unfortunately, I'm long since retired or otherwise inactive. Yeah, and the configuration is here. It's on Earth orbit, kind of following the Earth, and cartwheeling. I mean, of course, it rotates once a year around the Sun because it's on Earth orbit, and the lifetime of that instrument is 8 years, about somehow, not longer than that. Runs out of fuel. Yeah, fantastic scheme. But this has been now accepted as the ESA, European Space Agency kind of science project, and it's progressing. And the LISA Pathfinder is this satellite. It was sent to space 2015 and 2016. It demonstrated that the technology works, and actually it exceeded expectation. It worked much better than expected, so it really promised that things work. Now the frequency window, it's much bigger than LIGO. Then it observes much smaller frequencies. It's actually just at the right spot for this early universe gravitational waves. Here is the frequency. The LIGO is up here. It's about 100 Hertz. 100 times per second is the typical frequency, which is the frequency of the black hole spinning around each other. Here it's 1 millihertz or 100 hertz, so that 1 hour typical, or fractions of hour typical frequency scale where the LISA is sensitive. It is sensitive there to massive, this kind of galactic nucleus black holes, which are rotating and spiraling around each other, because they are of course much bigger, so that the times are slower. There's a third way to actually to measure gravitational waves at extremely low frequencies, which is the pulsar networks. Pulsars are neutron stars which are spinning in space and emitting radio pulses when they spin, because they have some kind of hotspot. They are extremely regular. I mean, they are extremely precise kind of clocks. And now, when you monitor many of these pulsars and the gravitational waves go through, the distance between us and the pulsar changes. And so that it means that sometimes you see it spin kind of frequency is higher and sometimes smaller with the typical sine wave. But of course they are very distant objects, so that the frequency is extremely small what you can do with this. These actually are active. They are active, these kind of pulsar timing arrays now, but nothing has been observed, so you probably haven't heard anything from them. And the objects seen by LISA are here. This is the LISA sensitivity. This is frequency. This is 100 of the hertz, 1000, so that 1000 seconds per one oscillation. And that's the sensitivity, this green band here. And the maximum is about 10 to minus 21, so that if you have 1 meter, or in this case this 2.5 million kilometers, I mean it's this fractional change what it can observe there. And there are many objects which produce gravitational waves here. Supermassive black holes, for example, here is million solar mass black holes rotating around each other. In some galactic nucleus that might be, and wherever in the universe they are, I mean, one cannot see it here because the pulses are so, and you can monitor them for a long time. I mean, month before the merger they are here, day before the merger, hour before the merger, and then boom, suddenly they hit each other and vanish there. And there are lots of binary star systems within our galaxy, what you can measure here, and they claim that there are thousands and thousands of binary stars here on this colored block, but they can kind of catch them all. I mean, they can just do the Fourier analysis of all of them and then find that individually can see them all, and that's why I kind of take them away. Cosmological signal, what it is here. It's a stochastic noise. Gravitational noise. Unfortunately, it's noise. Typically, these signals are kind of regular, kind of one note, boo, whereas cosmological signal is noise. And noise, of course, is much harder to observe than one note. And the noise then has some spectrum, I mean, which means that there is some amplitude at some particular frequency. And you have to understand all of this in order to kind of be sure that you are observing the noise, which is a signal and not due to just some kind of collective effect of these other sources. One can call this foreground. So, as I mentioned, the transition proceeds to supercooling. Critical bubble nucleation, when these bubbles are nucleated, and then they grow and collide. And if the latent heat and supercooling are large, then the process is violent. Superheated water is a good example. If you go to YouTube and look at superheating water, you see these experiments where people put distilled water on the microwave on a very smooth, clean glass. You can heat it up, and it heats up way beyond 100 degrees until it explodes. The latent heat is being released. And when I was a student, I actually calculated that, estimated that you can fill the whole universe with pure water, heat it, keep it at normal pressure, heat it to 110 degrees centigrade. The lifetime of the universe is not enough to make the bubbles to form. It's so metastable. The reason why water boils, of course, is the impurities what are in it. I mean, they act as nucleation centers. Or the boundaries, your kettle has edges, and those make it easier. But pure water universe doesn't have boundaries. There are no walls there, so that and it's pure by definition. Universe contains what it contains, so that it can have strong metastabilities. So our goal is to take a set of these BSM models, candidates, and there are many technical names which I don't go into here, and calculate how much they would produce gravitational waves and how they would be visible at LISA. Or conversely, how to use LISA observations to constrain these models. And this is a very worthy goal. I mean, this is exactly what is done in particle physics experiments. This is phenomenology of BSM theories. Now this is a bit technical and I think I should probably skip most of this, but let me mention quickly. I mean, there are many stages, many stages what we must master in order to make these predictions. We have to know the thermodynamics of this model, this candidate model, which means so-called equation of state or latent heat. What is the heat released when the transition happens? I mean, water has very big latent heat, for example. And then this critical bubble nucleation rate. And this is actually very important because this determines how deep you supercool and also gives you the length scale what is being generated. These bubbles nucleate and of course they have then specific distance from each other. They grow. But that gives kind of specific distance and specific frequency of the gravitational waves. And all technical details, the bubble wall fluid interaction. What I have marked here green means that this we know about. I mean, we can handle them. We know how to do it. There is a question mark here because this takes some work still to make work. And then at the last stage, we have to model the growth of these bubbles, collision of the bubbles, and what kind of flows, hydrodynamical flows they cause. Of course, it's filled with fluid, hot fluid, the universe at this stage. And when these bubbles grow, I mean, there's all kind of turbulence and hydrodynamical flows. And this requires numerical simulations, and that's what we have done here. We use effective theory. This is, of course, very much an effective theory which contains hydrodynamics and then some order parameter scalar field. And gravitational wave production here is straightforward to measure from the energy momentum, so-called energy momentum tensor, but let's not go into detail. Okay, when the bubble walls, I mean, this now describes my bubble wall, what moves here. I mean, the Higgs field, which I call now this order parameter field, in the hot phase is here, down here, and in this low temperature phase, it goes to up here to the higher values. It wants to go up here, but because this tunneling barrier, it cannot do it immediately. You have to nucleate these bubbles. And when bubbles are nucleated, then this wall starts to grow, I mean, move to this direction so that the field then drops in this true value. But now it's universe filled with matter, fluid, hot matter. It pushes the fluid. If the wall is slow enough, then it pushes the fluid in front of it. This kind of thing is called deflagration. Or if it is supersonic, it is faster than the speed of sound in the fluid, it's detonation. And then it actually drags the fluid behind it. But nevertheless, in both cases, when the bubble wall moves, it pushes the fluid or drags the fluid with it. So even when they collide, this fluid movement then causes lots of flows, all kind of flow patterns in the universe. And these flows then generate gravitational waves. So that the gravitational waves are generated in all stages here. Actually, when bubbles collide, these growing bubbles collide, that produces gravitational waves, but actually not so much, because it's clearly subleading. You also generate turbulent flows, which can be important. I'll return to that a little bit. But it seems that the dominant part is sound of the phase transition. Because when they grow, they cause compression waves in front of them. Compression wave is just sound. So it's really kind of the sound of the popping of these bubbles. And the important thing is that when the bubbles collide and hit each other and the system then is in this low temperature phase, these sound waves continue. they keep on running through the universe, and their lifetime is much longer than the lifetime of these bubbles. But they keep producing the gravitational waves. And that's the reason why this is really becomes the dominant source of the gravitational wave production. It's sooner, this is, yeah, okay, that's a couple of technical slides, what equation of motion we are solving here, how it is implemented. But let us now look at the simulations. Here is a snapshot of simulation. One, bubbles are nucleated, they grow and go on. Let me show a movie about one. It is a simulation volume. I mean, you can kind of see three-dimensional volume. It is empty now. This is in the kind of the hot, metastable hot phase. And then we run this code. Bubbles start to nucleate, they grow, and this is hit each other. And now the transition is completed. It's smooth, covered by the bubbles. But these sound waves, this is energy density. They plotted here so that you see kind of energy density waves crisscrossing, and they don't go away. I mean, simulation ended there, but that's why they go away. but physically, I mean, they sustain themselves for a long time. And these crisscrossing sound waves are the things that produce gravitational waves. Actually, I had much, I think, almost hypnotically nice plot here. Sorry. This full screen. Same process, but now seen in a little bit slower motion. Too slow. No. Now it grows. I mean, there's a bubble growing. This now shows the velocity, fluid velocity. Oh, sorry, fluid energy density, so that you don't see difference between the inner and outer part of the bubble. This is three-dimensional simulation, one slice through it. And you see bubbles are being nucleated, and they grow and hit each other all around the space. The growth speed is a fraction of the speed of light, so they are really growing very rapidly, of course in our units, but much lower still than the speed of light. It's a fraction of the speed of light. Now the transition has completed, the bubbles have swept through the whole space, but these shock waves, sound waves are still propagating there all over the place. And okay, I mean, yeah, it doesn't develop anymore in a way. It looks the same kind of as long as you run the simulation. But very interesting looking network of waves you obtain there. Pause this and go back here. The results are that we can measure the power spectrum of the system here. That's the wave number at the x-axis, and the gravitational wave, the amplitude on the y-axis. And depending on the speed of the wall, I mean, we get different shapes. If the bubble walls are moving with the speed of 0.8 in units of light speed, so almost at the speed, close to the speed of light, very fast moving walls, then we get one particular kind of shape of the gravitational wave power spectrum. However, if it moves close to the speed of sound there on the 0.56, then we get completely different power spectrum. And this can be in principle now used if we observe some kind of power spectra like that, I mean, that gives us information what happened there. So we can obtain thermodynamic parameters of the tail. And here is a model how one does it I mean, when we use this power spectrum and put it on the compare with the LISA sensitivity. Indeed, with some kind of prototype model, we can reach the LISA sensitivity region, so that in principle that is observable in this particular toy model. Here is what turbulence would give us, and that's this sound wave. So sound wave clearly dominates in a wide range of parameters. Oops, now I went too far. Okay, so the status so far. We still have not kind of done this full story. We have to do much more than we have done now. We know how to do this, how to obtain thermodynamics and thermodynamical quantities for any of these models. And it has been done, for example, in one particular version. This is for particle physicists know what that is. We know how to calculate bubble nucleation rate. That has been done for some kind of toy model, not the realistic model. How the bubble wall moves, the friction calculation needs still some development, but this is all in microscopic physics. This now must be fed to these simulations what I just showed. We can fix the parameters of this bubble growth and collision model, what we simulate then to produce the gravitational waves. And this whole chain has to be kind of done for a particular model in order to kind of obtain predictions for the model. I mean, how much that model produces gravitational waves. And we have done only kind of weak and medium strength transition, not strong transitions. But so far the results are very promising, and indeed it has to be continued. So to conclude with here, gravitational waves, they are a new way to study particle physics. So it's really VSM phenomenology. Yeah, and energy reach, what we can do here is much higher than in accelerators. And we know in principle how to do it, how to connect the model to the gravitational wave spectrum. There are many stages which are not fully done, but I mean in the future years we will do it. And we have kind of seen this, which was unanticipated before we started, that the gravitational waves are really produced by the sounds, and that can be order of magnitude larger than other mechanisms. So it's promising outcome for the observations. And also, this is of course, we are working in the context of LISA, but in principle of course this is also for any of the future or planned detectors, DESIGO, which is planned in Japan, and 2 Chinese detectors are also kind of on the planning stage. These are not kind of at the same level as LISA. LISA is kind of going forward, but these are still kind of PowerPoint detectors, but they have been seriously pursued anyway. An ultimate detector was this Big Bang observer, which was something like 10 years ago proposed. It's a huge constellation of 12 satellites which beam lasers to each other. And in principle that would have had enormously range in frequency and in strain on this how sensitive it is to the gravitational waves. But I mean that probably will never be realized. This kind of observatory is way too expensive and technically also probably impossible to do. But okay, thank you. I think this was my
questions?
We know there is a particle wave duality. So what is the particle name for gravitational waves? Or is it any?
Well, it's a graviton is the quantum of the gravitational waves. That has not been, of course, observed. I mean, the gravitational waves, what have been observed so far, are like waves in the ocean. I mean, you have huge classical gravitational waves, what are detectable. Single graviton carries so little, let's say, energy at these frequencies that it is completely unobservable. and I don't. I mean, unless you propose some kind of very exotic theory of gravity, I mean, I think it still remains. Peter?
In the LISA experiment, what does one do in order to keep the dimensions of that triangle constant within that error limit that you have there?
They are not kept constant. I mean, they are allowed to move, but you know how they should move. And then you kind of subtract from this movement this disturbance caused by the gravitational wave. So you just have to measure it to this accuracy, but not keep it constant. That would be probably impossible to keep it constant.
But even though you know Kepler's laws,
Yes.
that this system absorbs energy and gives energy away, which changes the configuration.
Yeah, that's true. But this is the one of the thing was this. I mean, why it is isolated from the external disturbances. That the inner part is not. I mean, it's enclosed in the outer part and free flying inside the inner part. So that the outer part protects it from radiation, dust, and so on. And also the frequency is the same. I mean, this triangle is big. It rotates once a year actually, whereas it measures once. I mean, millihertz. I mean, 1 hour frequencies, which is much higher frequency than these disturbances, gravitational disturbances would cause it. So that it seems to be under control. I mean, I trust the engineers.
More questions? Sorry, yes.
I have two questions. The first one is, like, after phase transition, right, you get the depth. So some particles becomes massive.
Yes.
So the energy density change. Will this one impact the like generates gravitational wave as well? And the second question is, how to say, if, as you say, you have different models, right? It's like minimal supersymmetry or 2SW model. They have different phase transition.
That's right.
So, do we have like, how to say, predictions to like, or like ability to tell which one is like the one you observe? Do we have like? I know it's dependent on model,
Yes.
but how do
I
you
mean, it's true that I mean, what you get from observations, if you observe something, you get some thermodynamic parameters, and you of course don't know which is the model which produces this. You can just get just a class of models which does produce these parameters. I mean, that's obvious. But I mean, all of these things that some particles might become massive in the phase transition, it's in principle taken into account in the thermodynamical parameters of the theory. So that when we fix the parameters of this final model, I mean, we calculate all of that, the desired accuracy.
So your bubbles are expanding in time, but could you imagine instabilities where they could also collapse and create something like sonoluminescence? I mean, releasing energy in that way?
Yeah, I mean, of course, I mean, at the final states, they do collapse, or they do, well, collapse in the sense that when the volume left, which is not swept by the bubbles, I mean, it's kind of negative bubble then, and that collapses. And at the very end stages, that can be very quick process. But sonoluminescence comes when the
Like when it's contracting, right?
contracting, yeah, and you have some light which bounces back and forth, and it's redshift, I mean, blue shifting somehow, I guess. Yeah, I mean, the similar kind of phenomena can happen here, but probably we don't have so many scales. Well, I'm not sure. I mean, interesting question. I mean, I should think about it. I don't.
Take into consideration I'm just a low energy guy.
Yeah. I mean, it's quite possible that something interesting could happen there. Offhand, I haven't thought about that feature. Yes.
So I have a technical. Are there further questions? So I have a technical. I mean, how much do the boundary conditions affect the actual, universe is pretty big.
Mhm.
How many bubbles you accommodate in the actual simulations?
Yeah, I mean the simulations of course are strongly constrained by just the computing power.
Yeah.
And we at most we had few thousand bubbles, and sometimes about 100. I mean we vary it a lot because then you look at the different kind of kinematic range when you have many bubbles or only few bubbles, then you allow them to kind of grow much more before they hit each other. And of course in a perfect world we would have, because in the real universe the range is enormous, I mean between the nucleated bubbles and when they collide there's an orders of magnitude scale separation. I mean from microscopic to macroscopic, and one cannot do it in a one numerical simulation, obviously it's impossible. But we try to of course estimate the effects of that.
Are there further questions? If not, let's thank again Kari.